My name is Mungi Park, and then I'm doing this presentation for Professor Mohammad Asadi, as he has had a good family issue, emergency. So last week he asked me to do this for him, and then I wish I could travel to the Penn State University because I've never been there, but it was not enough time for me to get a travel approval to. Okay, so I hope I can deliver 100% of the presentation for Professor Asadi. Okay, I'll be talking about today advanced batteries to decarbonize heavy transport. And all the contents I will talk about today is from a paper published in Science last year. The title of the paper is a room temperature rechargeable lithium-based lithium-air battery enabled by a solid-state electrolyte. Yeah, I'd like to introduce myself first before I start the introduction of the presentation. And I'm a postdoctoral fellow working at Argonne in Material Science Division. And then now I'm working on two research projects. The first one is from EREVTO, primarily for lithium superoxide-based lithium oxide batteries with my Argonne supervisor, Larry A. Curtis. And now I'm also working on, recently, Larry and Mohammad got the ARPA project funding jointly. So now Dr. Larry Curtis and Dr. Sania Tepasevich from Argonne and Professor Mohammad Asadi from IIT make a collaboration team. I'm leading the collaborated research team. So we aim to, this started from the science paper after it's published. And then the same concept, but from the science paper, I'll talk more about the details. Science paper achieved the high energy density that could be done like solid state electrolyte based lithium oxide battery. And then now we are targeting over the 1,000 watt-hour per kilogram of the energy density. So this is slide shows introduction. So we can just, it shows a comparison of lithium ion and lithium oxide battery, the chemistry. So basically the theoretical energy density of the lithium ion is around 700 watt-hour per kilogram. However, when you see the lithium, Li2O, we call this lithium. So Li2O is from the 4 electron reaction that could happen in the lithium oxide battery. I'll give them more details in the later slide about the chemistry. And it can show over 5,000, around 5,200 watt-hour per kilogram of energy density, which is very desirable for being used in heavy-duty vehicles. So from the science paper, it was achieved to have the 685 watt-hour per kilogram. And as I said, in the new ARPA project, we are targeting targeting to achieve the over 1,000, so 1K watt per kilogram of the energy density. So this slide shows a typical discharge product formation process. So you can see in the title, like 1 to 4 electrons. So which means there could be 1 electron reaction, 2 electron reaction, 4 electron reaction. And then after that, each number of electron reactions, there are going to be 3 different discharge products. The first one is a lithium superoxide through the 1 electron reaction. The 2 electron reaction which will form the lithium peroxide, the Li2O2. And then at the last of this step, there are going to be 4 electron reaction forming lithium, Li2O. However, it has been known that most of the lithium oxide battery research shows either lithium superoxide or lithium peroxide only, because we know that this reaction, the last step, this reaction includes 2 moles of electron, 2 moles of lithium. Compared to this process, it has more, it requires a higher energy barrier. So in this case, so far, it has been known that at room temperature, it's not possible to form the lithium, and it is not possible to do the 4-electron reaction. However, in this paper, we found that it could be done at room temperature. And 2018, the Linda Nader's group published a science paper with they could show the 4-electron reaction with the reversible 4-electron reaction at high temperature, so such as 150 Celsius. But in this paper, it shows room temperature 4-electron reaction possible, and then I will show the detailed results in the later slides. So I'd like to introduce the characterization. What's the typical characterization of how do we characterize this lithium discharge product that could be formed, that are formed in the lithium oxide battery research? There could be, we can use electron diffraction and X-ray diffraction as long as the discharge products such as lithium superoxide, peroxide, and lithium has a crystallinity. But if they are, they could be amorphous as well. So once regardless if their crystallinity or amorphous, DEMS and Raman can be used to detect the discharge product. At this point, DEMS is very important because DEMS is a tool with very straightforward and robust. So from here, I will give you more details later, but I'd like to briefly introduce the DEMS here. So as the lithium oxide battery, lithium air battery use the oxygen as a fuel. So during discharge, oxygen from the air goes into the battery at the cathode side, and we use the oxygen as a fuel. So oxygen is reduced during discharge, and then oxygen is evolved. So oxygen is evolved during charge because once the discharge product is dissociated during the charge, so that means we can measure the amount of consumed or evolved oxygen during discharge or charge respectively. So in that case, we can calculate the number of transferred electrons during the discharge, such as 1 to 4, close to 1 to 4. So in that case, we can get very clear evidence for what kind of discharge products formed during discharge of the specific lithium oxide battery. So this is another important characterization method, which is called the titration. So there are two types of different titrations. The first one is, we call it total lithium discharge product, which means it can titrate all the possible discharge products such as lithium peroxide, superoxide, and lithium. So when they react with the water molecules, the lithium hydroxide can be formed. And then that hydroxide, once the hydroxide is formed, we add hydrogen chloride, and then to form the lithium chloride. And by adding more the phenolphthalein into this solution, there are gonna be color changes. So by comparing that color changes, but we use a UV-based spectroscopy for get the color difference. And by comparing that amount with the calibration line, pre-obtained calibration line, we can quantify the amount of total lithium discharge product. And then second titration is going to be a lithium peroxide titration that literally specifically determine the amount of the lithium peroxide only. So from these reactions, the lithium peroxide only can form the hydrogen peroxide. So this is the same reaction. And then once the hydrogen peroxide is formed, we can add a titrant, which is called the titanium oxosulfate solution. And then once they react, there's gonna be a titanium peroxide complex, which has the yellow or orange color. So the concentration of color is depending on the amount of how much the lithium peroxide formed, and also directly related to the discharge capacity. So by quantifying the lithium peroxide and the total lithium discharge product, so we can see this equation to obtain the more accurate. Do you hear me now? Is that okay now? Just check. in the middle of the presentation, sorry. Okay, maybe, because I don't get a phone call. Okay, let's see. Let me keep doing that. Okay, so from this equation, the lithium can be obtained. The amount of the lithium can be obtained by subtracting lithium peroxide and lithium superoxide from the lithium total discharge product. However, we didn't get the amount of lithium superoxide here because lithium superoxide titration is hard because lithium superoxide is a very unstable material. And then actually now I'm working on using some other titrant, and Larry and myself are working on this lithium superoxide specific titration. But here we also can use the lithium peroxide titration method to quantify the amount of lithium superoxide, because lithium superoxide, as I said, is an unstable material, and then which means it is also empirically conformed. It can be, once we age the discharge the cathode either in argon or vacuum, the lithium superoxide usually typically the disproportionated to the lithium peroxide. So that means we can prepare two different discharge cathode. One is a fresh right after the discharge, and the other one is aged after aging. So then after the titration, second titration, quantify the amount of the peroxide, there's going to be a difference in the amount of the peroxide. And then that difference exactly came from the disproportionated lithium superoxide. So once we obtain these all three, we can know the approximate, but a little bit more accurate than others. We can quantify the amount of the lithium, Li2O, after the four electron reaction. So the summary of the characterization for lithium oxide battery, lithium discharge product. So even though it is amorphous, the DEMS Raman titration can detect the lithium superoxide and distinguish one from others. And only in case the discharge product has crystallinity, we can use the electron diffraction and the X-ray diffraction. So this slide shows the typical lithium oxide battery configuration. So left figure shows a lithium anode at the end, and then the other side is porous cathode. And the porous cathode consists of the gas diffusion layer and the catalyst layer. So as I said, lithium oxide battery, lithium air battery uses oxygen from the air, and oxygen should go into the cell. So at the end of the cathode, there's like a gas diffusion layer, and then gas is favorably should go into the cathode, and then there's a catalyst layer as well. So in this project, lithium anode and the cathode with the molybdenum phosphide nanoparticles with the carbon support was used as a catalyst and cathode. And here, this is a unique point. In this paper, in this research, Larry and Mohammad came up with a unique composite polymer electrolyte-based solid-state electrolyte by adopting the MPU-TMS. This is the full name of this material. We call this MPO only. And also the LGPS, the lithium, germanium, phosphorus, and sulfur. So this is one of the most popular, the sulfur-based solid electrolyte. So once they mixed these two materials, there was a reaction observed. So ether groups at the end of the MPU-TMS chain react with the sulfur groups. So they made a silane bonding. So once they are mixed, so LGPS surface, not a particle surface, is well protected by the MPU-TMS. And then by adding more, the long chain PEO and then lithium TFSI as a conductor, we could get the CPE, a new CPE for the lithium oxide battery. So this slide shows the composite polymer electrolyte property. So first of all, I'd like to say it was observed very high ionic conductivity, so 0.52 millisiemens per centimeter. And also this XPS, high resolution XPS, sulfur 2P and silicon 2P from both elements, we saw strong evidence for the bonding between sulfur and silicon, which is silane bonding. And electrochemical stability of the 5.27, so it shows a wide window for improved the stability of the solid state electrolyte, and also lithium transfer number was a 0.73, which is high and which is real consistent with the great ionic conductivity of this new type of solid state electrolyte. And this is the battery performance with the CPE-based solid electrolyte, and it's performed 1,000 cycles. And then you can see at the end of the 1,000 cycles, the discharge voltage is still high as 2.81 volt, and the charge potential is a 3.24 volt, having around 0.4 volt of overpotential, which indicates a very high energy efficiency. And also it showed the deep discharge of the 11 milliampere hour per square centimeter, which has a high potential for being used in heavy duty vehicles. Yeah, this slide is very important because our topic is the DEMS. So we use the in situ DEMS very effectively, I think. So from here, as I mentioned before, I'd like to give more details here about the DEMS. So as I said, we use oxygen from the air during discharge. The oxygen is reduced and then makes lithium discharge product solid. And then during charge, the solid discharge product is dissociated, and then to the lithium ions and oxygen gas. So especially during charge of the battery, we do the charge battery, and at the same time, we connect the DEMS at the end of the cell, and then we measure the amount of oxygen evolved during charge. So we use the known capacity, and we know what by quantifying the amount of oxygen, we can get to know the transferred number of electrons during the reaction. So the results showed from the CP-based solid electrolyte, we got like 3.94 electrons, almost like a 4-electron reaction. And also, ex-situ DEMS showed 3.97. And also we did the titration, as I said, shown before. The titration can quantify the amount of lithia. And then we got almost 100% of lithia, 98%. And then we got like we can calculate from that numbers, and then we know the discharge capacity. We can calculate the 3.96 of the electrons transferred during the discharge of the cell. So from this result, we could learn that, okay, at room temperature with the very specific optimized condition can make 4-electron reaction and form lithia as the major final discharge product. We also did the Raman spectroscopy as a function of time. So we found that as a function of time, like every 7.5 minutes, we got different discharge products. We got some peaks for discharge product. So lithia at around 495, and then lithium peroxide at around 795, and another peak for lithium superoxide at around 1125. And then by the time we saw the increasement of the peak, so we plot this difference in the intensity of the different peaks. And then this is the plotted figure. And then you can see from the start of the discharge to the 15 minutes, all the discharge products being increased looks like linearly. But after 15 minutes, the lithium superoxide, green color, the lithium peroxide, blue color, did not increase at all, like almost similar. But the lithium Li2O increased linearly. So from that point, we learned that from the in situ DEMS and titration, we got to know that, okay, this is a 4-electron reaction, and it looks like the lithium is the major product, major discharge product. And that's the result. And this can show every like 7.5 minutes, we do see how much the discharge product is grown by the time. So it can show us that the process of the discharge product formation. So from this point, we try to understand how exactly everything going on during the discharge process of the cell with the CPE, solid state electrolyte. And we try to analyze the cathode morphology, because all the discharge products usually grown on the cathode side. So from the SEM images, we can clearly see that there is no specific shape of the discharge product, which means most of the lithium oxide battery research, as I said, they have the lithium peroxide, Li2O2, as a major discharge product, and the lithium peroxide has a very typical toroidal structure of the discharge product. So, however, but in this case, we didn't see anything like that. We didn't see any like cubic structure, discharge product, anything like that. So we found that comparing this to SM images, we found that the valley, the pore side is kind of filled with and then we assumed that this could be discharge product. And then we did the Raman mapping. And then from the Raman mapping results, we found that MO3P has this this black is like a lower the height, which means it could be explained to be a valley on the surface of the cathode. And then looks like the lithium has filled that valley well, and then there are some lithium peroxide. So this can be, we try to explain and understand how the mechanism of the discharge product grows. So this right figure shows a side view illustration of the location, such as like valley and the discharge product, how it grows, and then how the composite polymer can provide the lithium ions. So for here, so Larry and Mohammad came up with a mechanism, which is called the sequential reaction interface, SRI mechanism. So this is important here. So we know that the surface, first of all, we need to know that there's a big difference between liquid electrolyte and solid state electrolyte, because in this case, we see the air, the open space, which means the solid state electrolyte cannot fill all the pores of the cathode. However, in the case of liquid electrolyte, as we use liquid, it can fill the pores. And then in that case, they're not going to be a open space like here. So this is the one unique part for the solid state electrolyte-based lithium oxide battery. And also, as I said, we need the right condition. So very specifically optimized condition, such as the lithium conduction should happen very well, and electron transfer should happen very well. So from here, we can see there is a CPE electrolyte. So lithium conduction happens through the CPE, and then electrons can be transferred from the cathode. So MO3P, the molybdenum phosphide coated cathode. And also from this open space, the oxygen can be provided. So they start, once the discharge of the cell starts, the discharge products start to be formed at this point, and then it grows along with the surface of the cathode. Sorry. It starts to be grown on the surface of the cathode, and it grows and grows and to the bottom of the valley. And then once, so Larry and Mohammad thought that, okay, once they fill all the surface, cover all the surface, it starts to be steady states. Like, for example, then it from the 0 minute to 15 minutes, and after 15 minutes, it starts to be steady state, means still the lithium peroxide is superoxide is ground, but once they are ground, when they formed, this reaction was very favorable, very fast, because of lithium conduction and electron transfer was very favorable. So formation of lithia was like facilitated. So that's the mechanism, the suggested mechanism by Larry and Mohammad. And because we got the lithia as a major discharge product through the 4-electron reaction we confirmed that from the in situ DEMS, Raman, and titration. So now we are working on another following project to get more explanation and more evidence for this SR reaction. And so far, we didn't publish the papers yet, but so far it's working fine, I think. Okay, this is so far we got 685 watt-hour per kilogram of the energy density, and now from the ARPA project, now we are targeting over 1,000 watt-hour per kilogram. And now we carefully consider the mass contribution and volume contribution of each components in the lithium-ion batteries. The RP project is going to be 3 years, and then 1 year and a half, and the other second phase is going to be the other 1 year and a half. And then once we get successful in lab scale first phase, and then there gonna be a second phase, and then which is very challenging because the second phase is gonna be a scaling up of this system. So this is the last slide for this presentation. We got an opportunity from the start, from the science paper published 2023. So from that point, from the start, we could get the new funding, the ARPA-E, and then this, I hope this can give some more opportunities in being used in heavy duty vehicles. However, we have some challenges, so we need to figure that out. But they are kind of the more cyclability and with the high discharge capacity and rates, and we also need as I said, comprehensive understanding of the morphology and the nature of discharge product to clarify the SRI mechanism. So we never used synchrotron-based and synchrotron-based and cryo-TM yet. So we think, based on the literature, we think to understand the discharge product mechanic, the growth mechanism, so such as cryo-TM and synchrotron-based tomography and X-ray imaging could be very helpful. And also there could be modeling, continuum modeling or machine learning for faster molecular dynamics and DFT. They are going to be very helpful. Yeah, I'd like to thank you to my supervisor, Larry A. Curtis, and then to Professor Mohammad Asadi, and then his team at IIT. Okay, thank you very much. How do I get the
Moon, I don't know if you can hear me there. Can you hear me clearly?
So maybe, should I stop chat?
Hi, Moon, can you hear me?
Oh, okay. I'll try.
Okay, right.
Yeah, looks like. Okay. Anyone can say?
I don't know. Can you hear me, Moon?
Oh, I hear you. I hear you now.
Oh,
Okay.
hey, thank you so much for taking time to join us this morning at short notice. Really appreciated.
How about now? Do you hear me?
Do we have any
Anyone hear
questions
me?
for Moon at all?
Hello? Hello?
Hey, Moon, can you hear me? Hello? Penn State to
Hello?
Moon. Penn State to Moon. Moon, do you copy?
Hello?
Hello, hello. You hear me?
Oh, do you hear me?
Yes, yes. You hear me? All right, very good. I got a couple of questions for you, but maybe I'll start with one and pass the mic. So you showed a plot that where you showed that the speciation of the lithium changes. I think during the sorry, now we can't hear you again. We can't hear you.
The
Oh,
audio.
now I hear you. Now I hear you.
Okay.
So I think it was on slide 10 or around slide 10. I failed to write down the slide number, but you showed how the speciation of the lithium changes during discharge. And I was curious if you could, and I believe this was Raman data that you used to make these conclusions. But I'm curious if you could also make a similar conclusion using a DEMS measurement, where you would partially discharge the device and then recharge while measuring the amount of oxygen evolved from the from the battery during the partial recharging. Have you thought about that sort of experiment at all? Oh, we can't hear you again.
Yeah, it looks
Here we go.
like
Here we
there
go.
is a two microphones, two speakers, and then somehow it can keep changes the. Do you hear me now?
Yes, yes.
Okay, I don't know. Yeah, so I think your question is like the time as a function of time that we did a Raman spectroscopy. You think we can try to use DEMS, right?
Yeah.
For this kind of things. Yeah. We are able to do the in situ DEMS. So we thought that in situ DEMS is the operando system. Like we can do it in situ. So how do I say it? So we never thought about that kind of things. Every 15 minutes, every 20 minutes, doing that DEMS to obtain the gas evolution, quantify the gas. Yeah, so we thought that in situ DEMS was enough.
I see.
But yeah, but we can we can think about that.
Yeah, it
later.
seems like based on your result that you would expect a different number of, ratio of oxygen evolved to electrons transferred, that would change near in the final moments of recharging. Since when you're recharging the battery, based on the curve that, if I understand correctly, and the final moments of recharging, you convert the lithium, the LiO and the LiO2 back to lithium metal. And so that ratio may change, but I'm no battery expert.
So you're asking you. So can you say it again, please? What was your question in this case? So you think,
Sorry, I'm getting the mic back. So it may be easier to understand if you had the slideshow still up, but you showed that during the discharge of the battery, that the lithium metal is first converted into LiO and LiO2, and also Li2O, but that
yes.
the LiO and the LiO2 quickly plateau, and that over long discharging, the Li2O is predominantly the form of lithium oxide that is created. And so I was curious to know, if you then fully discharge the battery and then fully recharge the battery, it seems likely that for the majority of the recharging period, you would predominantly evolve, I guess it would be 4 electrons per O2 evolved during the recharge. But then in the final moments of recharging, since you're converting the LiO and the LiO2, that ratio would change.
It could be or it could be not, because every time we do the discharge of battery. So for example, once we do the discharge battery with the fixed capacity, for example, 0.1 milliampere hour per square centimeter or 1 milliampere per square centimeter, we do the same capacity charge. So we didn't do, I think as far as I know, authors didn't do the titration or DEMS after the long discharge. I mean, full discharge in you're saying means like a deep discharge, right? So in that case, this is a big difference from the lithium-ion battery. So we use the oxygen from the air. So it is kind of, we can say it's unlimited fuel. So in the metal air battery, once we do discharge, we don't know what's the maximum discharge, 100% discharge. So it is kind of, hard. So that's why we don't use the DOD, depth discharge in metal air batteries. So we don't know. So it really depends on the battery chemistry and then some possible side reactions. So now we are trying to, as I said in the previous slides, we could achieve the 11 milliampere hour per square centimeter of discharge capacity. But now we are trying to get higher, but we don't know. So that could be done by optimizing the solid electrolyte. Also, that could be done optimizing the cathode. So in that case, we always do, like this case, we always do, when we want to analyze and characterize the discharge product and like using the in situ DEMS and Raman and titration, we always determine what fixed capacity we are going to use.
I see.
So in a case, so we can try the longest capacity, like 10 or 15, because when we try, because they are different experiments. So once we use the fixed capacity, we decide 1, 2, 5, something like that, and then once we do deep discharge, we don't know how long the discharge is going to be.
Nice.
So yeah, and I think after charge, we never done this before, but if the lithium Li2O is the major final product, I just expect we could get a large amount of Li2O, but may not be around the 98%. It could be lower, I think, because long discharge usually very, very challenging. So there could be some side product, such as there could be some degradation of the solid state electrolyte and degradation of the cathode and catalyst. So once the discharge capacity is longer, so we expect then there could be some unwanted things. Then that would affect the lower amount of discharge products, such as lithium, I think.
Okay, thank you so much, Moon.
Thank you. Is that all?
I believe so. Any questions online at all, Aaron? No, I think we're all good, Moon, but thank you again.
Thank you very much for your attention. Okay. Have a good one.